We're going to talk about bond energies. We can use bond energies to estimate energy changes in reactions. So we've already looked at how we can calculate a heat of formation or a heat of reaction from heats of formation. We can also do this using bond energies. Well, what is a bond energy? What is bond energy? It's the energy required to break 1 mole of the bond in the gas phase. We don't have to worry about the small print in the gas phase, but it's the energy to break 1 mole of that particular kind of bond. Bond energies are always positive. It always requires energy putting into the molecule to break them. If it takes more energy to break, that means that the bond is stronger, right? Here's an example of a chemical equation describing breaking a bond. So here we have HCl in the gas phase. Here we have a hydrogen atom and a chlorine atom. There's no ionization or anything that happens here. All we have is that hydrogen-chlorine bond existed here and now it's gone. And that requires the input of 431 kilojoules of energy to break 1 mole of those bonds. If compounds have strong bonds, they're more stable because it requires more force to break, more energy to break the bonds. Does that make sense? Sort of like the 3 little pigs. Remember that story? With the house of straw and the house of wood and the house of bricks. A house of straw, a house built out of straw doesn't take much energy to break down, right? A house of bricks takes a lot of energy. So compounds that have stronger bonds are more stable and tend to be less reactive. Well, bond energies are going to be slightly different depending on the compound that particular bond is in. And so we use an average bond energy. We can look at a carbon-hydrogen bond, and if we see this carbon-hydrogen bond in the molecule methane, the bond energy is 438. If we put some fluorines on there, trifluoromethane, then it's 446. Tribromomethane, 402. Trichloromethane, 401. So depending on the other things that are bonded to that carbon atom, the carbon-hydrogen bond may be stronger or weaker. And instead of trying to deal with all these zillions of different kinds of bonds, we're just looking at an average bond energy. Because when we use these to estimate enthalpies of reaction, it's going to be an estimate. So we look at the average carbon-hydrogen bond energy, 414. Now, double and triple bonds are stronger, and so they have larger, higher bond energies than single bonds do. So here's a table from your textbook showing a bunch of different bond energies. So when you need a bond energy, you just go look it up. So if I need a hydrogen-nitrogen single bond, there it is, 389. Notice here we've got nitrogen-nitrogen bonds, single, double, and triple. And the bond energy increases, 163, 418, and a triple bond is 946. It's a lot stronger. The one weird one I'd like to point out to you is the carbon-oxygen double bond. See that asterisk there? So this is 736, except if you're looking at CO2. If you're looking at CO2, then it's 799. CO2 is a very common molecule, and the difference there is somewhat significant, and so it's listed. Well, how do we use bond energies for estimating enthalpy changes? What we're doing is we're looking at breaking bonds and making bonds. Breaking bonds is endothermic, putting energy into the molecule. Forming bonds is exothermic, releasing energy. So we're going to look at all the bonds that get broken. That's energy putting in. And we're going to subtract the energies for all the bonds that get formed, because that's releasing energy. And that gives us an estimate of the enthalpy. So it can be expressed this way. the heat of reaction or the enthalpy of reaction is the sum of all the bond energies that are for the bonds that are broken, plus the bond energies for the bonds that are formed. These will be negative, okay, because it releases energy. We'll look at a simple example here. This looks a little like a Born-Haber cycle, and it really is the same idea. It's all based on Hess's law. If you can look at the energy changes in a series of steps, you can put those together and look at the overall energy change, even though that's not how it occurs, because it's a state function. So here we have methane and chlorine, and those are reacting to form hydrogen chloride and chloromethane. So what happens here? Well, a carbon-hydrogen bond has to get broken, and this chlorine-chlorine bond has to break. So that requires an input of energy to break those two bonds. Then what happens is we form a chlorine-carbon bond to make the chloromethane, and we form a chlorine-hydrogen bond. And so that releases energy. So there's an input of energy and a release of energy. It's sort of like making an investment. If you want to make money, you have to spend some money, right? So you put money into whatever it is you're investing in, and hopefully it will give out more money than you put in. The difference here would be your profit. That's the heat of reaction. So we often talk about energy being stored in chemical bonds. I refer to that as chemical energy, a form of potential energy. Breaking a bond, though, always requires energy. An energy-rich compound, one that has a lot of chemical energy, can undergo a reaction where weak bonds are broken and strong bonds are formed. The energy gets released when those strong bonds are formed. So compounds that have weak bonds actually are higher in chemical potential energy. It's the forming of the chemical bonds that releases the energy. So let's do an example. A potential future fuel is methanol. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion in kilograms per mole. Okay, so equation for combustion. So we were given the formula there. So we've got CH3OH. And what's the other reactant? Oxygen. Can't burn things without oxygen. What are the products that form? Carbon dioxide and water. Because I told you so. So you just, that's what happens. We have to balance this. One carbon. 4 hydrogens here, so we'll put a 2 in front of the water. And then we've got oxygens. There's 1, 2, 3 over there, and there's 4 over here. Awesome. So we could balance this by putting 3 halves here, right? We need a total of 4. There's 1 here, and then this one's going to be coming in pairs, so we could use a fraction. If you don't like fractions, what we've got here is an odd-even problem, right? Over here, we've got an even number, and over here, we've got an odd number. This one's even, so let's just double everything and see if that helps, because we need to double that one. We'll double that. I'm going to leave the oxygen alone, double this, and double this one. 2 carbons on each side, 8 hydrogens, and now let's look at our oxygens. 4 oxygens there, and 4 here. So now we've got 8 oxygens. And then over here, there's 2 in the methanol. And what do we need here to get 8? 6? 2 plus 6 would be 8. And so if we put a 3 here, we can get 6 oxygens. This balancing reactions business never goes away. Okay. So that was step 1. We're supposed to calculate or estimate the enthalpy of combustion using bond energies. Two times 8, I mean 2 times 4.
Okay, it's all the whole thing.
It's the whole thing, yeah.
Oh, okay.
Yeah. It can be a little confusing when we put this H over here, but writing it that way tells me that that's an alcohol as opposed to something else. Not sure what else that could be, but anyway. So you look at this and you're like, I don't know what bonds are being made, what bonds are being broken. It's not obvious. We need Lewis structures. So we need to look at the Lewis structures. And there's 2 ways you could approach this. One way would be to look at the Lewis structures and figure out which specific bonds get broken and which specific bonds get made. I find that tedious and it requires way too much thinking. I'd rather do like just a blast it method where we just imagine breaking all the bonds and forming all the bonds, right? That way we don't have to pick and choose, oh, is this one broken or that one? We're just going to break all of them and make all of them. So that's the approach I'm going to use. So we need to look at the Lewis structures because we need to know what sorts of bonds we have. Are they single? Are they double? What's connected? So the point of this is not to go over drawing Lewis structures. So I'm going to do this fairly quickly. That's the Lewis structure for methanol. And oxygen has a double bond. And then over here we've got CO2. We've done that one before. And we've got water. I just put the lone pairs in there so we can see that these are correct. They've got the right number of, everybody's got an octet. So we're going to look at this molecule, and there are 3 carbon-hydrogen bonds, 1 carbon-oxygen single bond, and 1 oxygen-hydrogen single bond. So I'm going to make a list of that. I didn't leave myself a lot of room. It's okay. So I've got hydrogen-carbon. I've got carbon-oxygen, and I've got oxygen-hydrogen. And then in the O2, I've got oxygen-oxygen double bond. Each of these requires energy. If I have 2 bonds, it requires twice as much energy, so I need to know how many of these I have. I have 2 moles of methanol. In 1 mole of methanol, I have, well, let's just start with an easy one. In 1 mole of methanol, I have 1 mole of OH bonds. In 2 moles, I have 2 moles of OH bonds, right? So the OH is going to be 2 times the bond energy. How many carbon-oxygen bonds are in each mole? 1. And how many moles do I have? 2. So 2 times 1 is 2. So I have 2 moles of those. How many carbon-hydrogen bonds in 1 mole of this? 3. 3 moles, right? There are 2 of them though, so 6 moles. So 6 moles of that. And I've got 3 oxygen molecules. So I have 3 moles of oxygen-oxygen double bonds. So did I put it up here? No, I didn't. We have to go back and look some of these up. I'm going to write them on the chalkboard because I am. Hydrogen carbon. is 414. Hydrogen oxygen is 464. Oxygen oxygen double 498. And then the carbon oxygen is 360. So I'll go back to my work. So I have 6 moles of carbon hydrogen bonds. So I looked that up. It's 414 kilojoules per mole. I'm multiplying by 6 moles. So maybe we should probably put the kilojoules in here. And I have 2 moles of carbon oxygen bonds, 360 kilojoules. I have hydrogen oxygen, 2 of those, 464. And oxygen oxygen double bond, 498. So I have some multiplying to do. That's 6 times 414, 2484. And then I've got 2 times 360, 720. And 2 times 464, 928. 3 times 498, 1494. And then I'm going to add those up. $46.98. Anyone else doing that with me? You were doing it. Why should I do it? No, I left one out, I think. Yeah, I left out adding the 928. Yeah. 5626? Yeah. Oh, what the heck. 5626 kilojoules. That's the investment required. Instead of trying to figure out, oh, well, what do I need to take apart? We're going to take all the Legos apart and start from just loose Legos, loose atoms. Okay, now we're going to go over to the product side and see what happens. So we've got some bonds over here. We've got carbon-oxygen double bond, and we've got hydrogen-oxygen single bond. And those are the only kinds of bonds we have. We have to figure out how many. We have 2 moles of CO2. Every mole of CO2 has 2 of those bonds. 2 times 2 is 4. So 4 times the energy of that one. In a water molecule, we have 2 of these hydrogen-oxygen bonds. We have 4 water molecules, so there's going to be 8 of those. Now, I already have the hydrogen-oxygen value, so I can put that one in. That's 464. But I need the carbon oxygen double bond in carbon dioxide. And that's the one at the bottom, 799. Am I putting energy in or taking energy out? Releasing energy? releasing energy. All of these should be negative. I forgot that. So I'll put my minus in front of that then. These need to be negative because it's releasing energy. So 4 times 799, that's going to release minus 3196 kilojoules. And I've got 8 of the 464s. That's going to release 3712 kilojoules. Add those together, minus 6908 kilojoules. Down here, this is the energy required to break the bonds, all of them, and this is the energy that's released when all the bonds that are made are made. So the estimate of this enthalpy, I would take 5626 kilojoules, and I'm adding that negative 6908 kilojoules. Negative 1282 kilojoules. Is that kilojoules per mole? No, it's kilojoules. This is the heat of reaction for this reaction as written. Because I did this calculation for 2 moles of methanol, 3 moles of oxygen, 2 moles of carbon dioxide, 4 moles of water. This is asking for enthalpy of combustion of methanol in kilojoules per mole. Kilojoules per mole of what? Probably the methanol, right? We're talking about burning the methanol. We're wondering, how many kilojoules do I get for every mole of methanol? So this amount of energy is released when how many moles of methanol burn? 2. So I need to divide this by 2 moles of methanol. So negative 641. Kilojoules per mole. Any questions? There's some details in there, huh? So a question like this is very likely to show up on your next exam, probably as one of the show your work problems. Because I'd like to give you partial credit if you just forget to divide by 2 moles, or if you just get the sign backwards. I'd hate for you to lose all the points, right, if you've got most of it right. Any questions about that? Bond lengths are somewhat related to bond energies. We can talk about an average bond length, and so we're going to look at the length of bonds between those 2 particular atoms in a bunch of different molecules and average them, just like we do with the bond energies. What we find is that single bonds are longer, double bonds are shorter, and triple bonds are even shorter. So here in this table, we're comparing carbon bonds, triple, double, single. The triple bond is the shortest, and it's also the strongest. The double bond is in the middle for both, and the carbon single bond is the longest and the weakest. So longer bonds are generally weaker, but of course there are exceptions, because there's got to be exceptions to everything, right? Here are some average bond lengths. Just in a table. I don't know what else to say about that one.